Good morning everyone, this is Rajasuji from first semester physics. In this video I am going to explain about the delta variation. So let's get into the video. And these are the table of content which I am going to brief into the video. So in the early development, in the early ages, Leonard Euler, he was a Swiss mathematician and a physicist. He introduced variation principle in mechanics by using the concept of virtual displacement. And then Joseph Louis Lagrange, he was a Italian mathematician and physicist. He introduced the delta notation for virtual displacement and he formulated the Lagrangian formulation, that is del L equal to 0. And then William Rover Hamilton, he developed mechanics using the delta notation, and then he derived the Hamilton equation, which is very familiar to us, that is dou p by dou t is equal to minus dou h by dou q, and then dou q by dou t is equal to dou h by dou p. And in later development is done by the Carl Gustav Jacobi and M.E. Noether. So Carl Gustav Jacobi, he was a German mathematician and he is known for Jacobi's operator, Jacobi transform and Hamilton-Jacobi equation, and he developed the theory of variational principles. And then Emmy Noether, and she was a German mathematician. She showed the connection between the symmetries and conservation laws using the delta notation. And then what is delta variation? So, delta variation is nothing but it is used to describe small changes in a system configuration or a motion, and then it represents the infinitesimal variation in the quantity, that is position, velocity, acceleration, time, momentum, and the energy. So, another question is why delta variation introduced into the classical mechanics? It is that to formalize the virtual work, that is delta represented an infinitesimal change in position, allowing for a precise definition of virtual work, and then to develop the variational principles. uh, these delta enable the formulation of principles like Hamilton principle, and which states that action integral is stationary, that is dou s is equal to 0, and then also to unify the differential equation, that provide a unified framework for differential equation and encompassing the various mechanical system. To simplify the complex systems, delta variations also help to analyze complex system by breaking down motions into small and manageable parts. And then properties of delta variation. So there are several properties, but the major important properties are the physical properties and the geometrical properties. In the physical property, the first one is infinitesimality, that is delta is an extremely small quantity. And then second is virtuality. So delta represents a hypothetical change. And then reversibility, delta can be reversed. And the locality, delta only affect the immediate neighborhood. uh, Another property was a geometrical property. It is divided into two, that is invariance and covariance. So delta is invariant under the coordinate transformation, and delta transforms covariantly under the coordinate transformations text. And then the derivation of delta variation. So in this figure we are going to uh, explain. We see that here the delta variation is a general type of variation path of system in which the time as well as the position coordinate vary in configuration space. So the end space of the path, that is the position coordinates, are kept fixed while the time coordinates remains change. So let's look into this diagram. Here A, B, C are the actual path, and A dash, B dash, C dash be the varied path. The end points of the path A and C take the positions A dash and C dash after the change in time, that is delta t, such that there is no change in position coordinates here. And then the point B actually takes the uh, uh, path from the actual path to the B dash on the varied path, such that the equation 1 can be written as qy dash is equal to qy plus del qi is equal to qy plus capital del qy plus q dot I del t. And then the variation of any function. This can be written as the second equation, that is del f is equal to summation I dou f by dou qi del qi plus dou f by del qi into del qi plus dou f by dou t into del t. Mm, And then using the equation 1, the equation 2 can be written as del f is equal to summation of dou f by dou qi into del qi plus q dot I del t plus summation I dou f by dou qi into del q dot I plus q double dot I del t plus dou f by dou t into del t. So, rearranging the equation 3, the equation 3 can be written as del f is equal to summation I dou f by dou qi del qi plus dou f by dou q dot I del q dot I plus summation of dou f by dou qi q dot I plus dou f by dou q dot I q double dot I plus dou f by dou t into del t. So the above equation can be changed into uh, del f plus capital del t df by dt, that is the equation 4, and thus the small del and capital del operations are connected by the relation equation 5, that is delta is equal to small delta plus delta t d by dt. And then the role of delta variation, um, there are several rules. First one is the variational principle, and it is used to derive the Euler-Lagrange equation, Hamilton principle, and Hamilton-Jacobi equation. And then the equation of motions. It helps to derive the equation of motion for the complex system. And then in the conservation law, it is also used to derive the conservation laws such as energy, momentum, and angular momentum. And then in the symmetries, it helps to identify symmetries in the physical system. Application of delta variation. So the application of delta variation is in various fields. So some of the fields are celestial mechanics. Delta variation studies orbital dynamics and stability. Perturbation theory based on delta variation analyzes the effect of small changes on celestial system. And then rigid body dynamics. Here Euler's equations derived using delta variation govern rigid body motion, and then delta analyzes the angular momentum conservation. In the fluid dynamics, delta variation applies to fluid dynamics where Lagrangian and Hamiltonian formulations are used. And then in the vibration and oscillations, these delta variation analyzes stability and normal modes in vibrational system. So conclusions. What are the conclusions? Here the conclusion is delta variation is a powerful tool in classical mechanics, facilitating the analysis and solution of complex problems. And then its applications is range from dynamical system to optimization, conservation laws, field theory, and rigid body dynamics also. Understanding delta variation is essential for researchers and physicists seeking to unravel the intricacies of classical mechanics. Here I attached some reference which I get into it, so you can also refer these books. And then thank you for spending your valuable time.